Thank you very much, gentlemen. Following to the presentation on situational awareness, join us to the InSpace into 3.0, which is scheduled today at 2:15 hours. And for the same, can we have the video, please? You can register yourself to join the exercise. And for the same, the scan is at the registration code. So this is scheduled today at 14:15 hours, which will be the post-lunch. And you can register yourself at the scan code, which is there at the registration desk. We move ahead to the next session, which is on advancing sensors, subsystems, and payloads for the space application. This panel will explore the critical role of the sensor, subsystems, and payloads in space applications. Industry experts will discuss innovative approaches to designing and manufacturing sensors for various space platforms, emphasizing their significance in enhancing data collection and operational capabilities. The discussion will cover advancement in sensor technologies, integration challenges, and the impact of these innovations across multiple applications, including Earth observation and defense. Participants will gain insights into how these subsystems contribute to the overall effectiveness of the space mission and the importance of developing a robust domestic sensor manufacturing ecosystem in India. For the same, the chair and moderator of the session, Air Marshal G S Bedi, former Director General, Inspection and Safety, IAF. The panelist, Mr. Rakshit Bhatt, co-founder and VP, Product Development, Galaxy I Space. Mr. Rupesh G, CEO XG Links. Mr. Yogeshwaran J, VP of Engineering, Astrogate Labs. And Mr. Siddesh Naik, founder, ULook Technologies. Over to you, Chair. Over to you, Chair. Thank you.
Okay. Good afternoon, ladies and gentlemen. It's a privilege to be here. Thanks to SIA, Dr. Rao, General Pannu, and Rajiv, who have put in a lot of effort and given me opportunity to chair this session. A decent audience, and somebody was complaining that audience thinning or thicker. I am always happy as long as the number of people are more than the Indian satellites in space. So we are, it's a good scene, and I think the people who are interested in the stuff need to be here. And, while I say privilege to be chairing this session, in the Indian Air Force, you guys must have seen close formation, people close forming on the aircraft. There is a lead aircraft and then everybody is sticking to it, 4, 5, 6, 7. It's a very tedious job. Close forming on a platform moving 900 kilometers an hour is very tricky and needs a great amount of expertise. And the leader generally has to fly, the way he wants. And this joke in the Air Force goes that anyone who doesn't know how to close form well, you make him leader of the formation. So chairing this session, I think the way General Pannu curates it, he gives a subject, then he asks people to send their ideas, he goes through them, and then he knows whom to, declare leader or chair of the session. Anyway, this is not to undermine the, potential or the competence of predecessors. In reality, the truth is quite different. Coming to the subject, we have advancing sensor subsystems and payloads for space application. We just had a brilliant presentation on C4 ISR. And that wants me to correlate that in the year 2002, in a conference in the United States on the theme of same C4 ISR, where the industry was highlighting various capabilities in war fighting, just like the way, we are doing today. Then General John Philip Jumper, the then US Air Force Chief, made a simple remark at the end of it, while people were trying to impress him. He said, and I quote, "Sum of all wisdom is cursor over the target," unquote. He implied, and in that he conveyed to the industry that any technology in whatever form, if does not help me to put my weapon over the target accurately, directly or indirectly, then it's of no use. 8 years later, Massachusetts Institute of Technology, Research and Engineering developed the application COT, cursor over target, inspired by the address of the chief. That is the time frame it takes for an idea to evolve into action when you seriously work over it. Now, taking this analogy forward, whatever sensors we talk of, if ultimately they do not help the commanders, whether fighting in the field or in the planning function, to wage effective war and win it, then their mere technical specifications do not really mean anything. They not only have to be effective in themselves, they also need to interoperate with the sensors in the environment. Now, sensing is something of great significance. Nature has provided sensors to living beings depending on the environment they are in. Traditionally, we say in human beings, we have 5 senses, and then people say that some of us develop the 6th sense, which has to be developed and cultivated, and I would simply call it that it is nothing but integration of all the 5 senses that has been given naturally to you, and then when you integrate them well, you develop the 6th sense. Okay, now sensors in general and more so in space application are indeed very important, crucial and vital, not because it's the topic of my session, but because they are going to play a decisive role in the future battles. Now, what are they? I will just read out a statement that the field of space-based sensors and payloads is undergoing rapid evolution, driven by technological innovations and the growing demands of space exploration and Earth observation missions. These advancements are reshaping our capabilities in space and opening new frontiers for specific discovery and practical applications. So says the ChatGPT. Now, why ChatGPT? Why did I, go to ChatGPT to, let's say, give me a problem statement? Because for the past 2 days, I have been overwhelmed and I have been convinced that AI is going to help commanders to win the war. They are AI-driven tools. Something like these tools, will give me quick and timely decision-making capability. Now, if AI or tools like this were going to help us win war of the futures, then I think we start training ourselves in that field better. And I said better to start with developing a problem statement for my seminar, at least from the ChatGPT. But now, to paraphrase it, okay, and since I must intervene with my own intelligence, I see that at its heart lies two phrases: technological innovation and growing demands. And all these demands, the problem would be simpler if they were kind of linear in nature or moving in one direction, then technology can catch up. But the problem, alas, is not the same. Demands invariably, they don't move in one direction, they move in opposite direction, covering wide spectrum. For example, take the demand for miniaturization and simultaneously enhancing functionality. Like if a box was producing some capability and you only demanded high capability, then I could keep making the box bigger and bigger, giving you the higher capability. But no, that's not the demand. The demand is I want smaller box with higher capability. So that is where the technological challenge comes. Then we want larger footprint with improved accuracy. With same number of satellites, I want shorter revisit time, meaning greater tilt, but better resolution at the same time. I also need to locate objects almost stationary like drones, as well as hypersonic missiles. We just heard a talk on that through the space sensors. Then ultra cool quantum sensors for faint detections. Okay. Now, in a nutshell, these advancements are aimed at such as improving PNT accuracy, enhancing environmental monitoring, and enabling more efficient and cost-effective missions. But nothing comes without challenges. Few of them like radiation hardening of space sensors, power efficiency to extend mission life, data download and processing ability to accommodate large data generated by improved sensors, and above all, integration of sensors, not only inter-vehicle or even intra-vehicle. Now that is why we have capable industry with us. They are all masters in their own field, and I will introduce them one by one briefly as I approach one of them. And my first speaker, I would go to Mr. Siddesh Naik. Mr. Siddesh Naik is the CEO and co-founder of ULOOK, pioneering satellite swarm technologies for ISR applications. He co-founded AXA, Earth Observation and Celestial Navigation, and contributed to transformative projects at New Space Research and Technologies, including HAPS and UAV swarms. Former graduate researcher in the US, he worked for NASA-sponsored CubeSat missions and specialized in astrodynamics. Now at ULOOK, he is advancing space-based RF intelligence, very capable person. Now, Mr. Naik, while we talk about different sensors, optical IRs are their individual capability notwithstanding, correlation of their input becomes vital. And of course, it can't be one by one, it has to be simultaneous in real time. A significant emphasis is being laid on tip and cue, bringing the importance of RF detection upfront. But RF detection is not just detecting a signal, its identification and its fingerprinting is equally important. Now, I believe you guys have done quite a bit of work on that. I would like you to tell us that how's your company doing this and what is it doing and what is there for our audience to take.
Perfect. Do you mind if I speak from the...
Oh, yes, please. I would request that, time-wise we stick between about 5 to 7 minutes so that we can indulge in question answers.
Hello. Thank you, Marshal Bedi. Pleasure to be here. Thank SIA for giving this opportunity. Right at the outset, let me address the difference between swarms and constellations. As we know, constellations are something we use to increase revisits over a given area. In comparison to that, swarms are clusters of satellites that are in close proximity with each other. They work in coordination with each other. They collaborate with each other. Right? So at a high level, that's sort of a difference between a swarm and a constellation. Now, it's interesting to note that the first satellite swarm mission is something that was demonstrated in August of 2023. This was through NASA Ames. Interestingly, in February of 2023, way earlier, our Defense Space Agency, DSA, they ran Mission 35 as part of the mission DefSpace Challenge, which was towards demonstrating autonomous CubeSat swarms. So for a change, and as a surprise, the lot of things that we're doing in terms of traditional space, but we're also looking at sort of emerging tech and sort of where the future is going to be. So with that, and before deep diving into swarms and sensors, what I'll do is I'll take a quick overview of nanosatellites, right, or small satellites. Typically, the decade of 2000 to 2010 was more of an educational platform or a decade. 2010, 2020 was more of a tech demonstrator sort of decade globally. What we're seeing now is sort of the operational realm, right? Operational phase that everybody's sort of entering into. There are private entities across the globe which have, and barring somebody like Starlink, which has 1,000+ satellites, there are a lot of commercial private companies with ISR capabilities, with assets more than 150 plus that are currently orbiting the Earth. Now, with comparison to that and sort of where we stand, it's sort of a time for us to also sort of retrospect and introspect and sort of take a look at where we stand. In terms of what we do at Uluk, our larger focus is to develop these swarms and more specifically heterogeneous swarms. As Bedi sir sort of referred to, as Chair referred to earlier, it's important for us to have a multi-layered approach. So to give context, and why do I say that? Let's look at a first layer, say which is RF. Now, a typical fingerprint of, say, a high resolution imager is something to the order of 10 by 10, 10 by 20 kilometers. You start going to SAR, it sort of starts expanding. You go up to 10 by 120, 100, depending on what sort of class of satellite system you're referring to. When you start coming to RF, your instantaneous FOV or sort of footprint could go as high as 1,000 by 1,000 kilometers. So if your problem statement is to have a good, is your MDA of IOR region, then sort of a no-brainer, right? You're sort of looking for a needle in a haystack, and there's no point using a telescope, which is what using a high-resolution imager would akin to. What you need really is a magnifying glass. A magnifying glass, which in this instance is the RF sensor, which tells you, say, down to a 200 by 200 or 500 by 500 meter, a sort of geolocation where your objects of interest or targets of interest could be. You then task the next layer, which could be SAR or imaging layer, depending on what your target of interest is, and then sort of do that extra investigation and figure out what it is. So RF, again, we have to sort of be very efficient in terms of how we're using our satellite layer. And this is where the whole tip and queue philosophy starts coming in. As we currently speak, there are RF companies, there are satellite imagery companies which are collaborating offline with each other. In the coming years, we're going to see this tip and queue with edge processing, with optical comm, with ISLs. This is going to move to space. So one asset class is going to tip and queue the next asset class, and you're going to start looking at a near persistent ISR picture, right? And we're going to come down to getting insights down to a few tens of minutes compared to hours that we're currently looking at. Specifically looking at what we are currently building on, we're building RF fingerprinting payload, and we're sort of going through our journey in terms for the TRL-9 journey, in terms of starting with a tethered drone tests that are currently underway for us. We intend to, again, test this payload at a technology demonstrator HAPS category of platform around 10 kilometers, and then eventually take it to space. Now, classically, RF and even the existing constellations, a lot of focus has been towards more of spectrum monitoring or emissions monitoring. It's to generally identify emissions in a certain frequency and then alert the respective user. What we are aiming to do is fingerprint from space, and to be specific, RF fingerprinting. As to sort of give a background of what RF fingerprinting here means is, say I have 10 receivers, same make, same model, coming out of same manufacturing line. When I try to fingerprint them, all 10 of them are going to have very unique, distinct RF fingerprints, which is again a function of their exposure to weather, manufacturing inconsistencies, the components that make up these transmitters. These could be oscillators, amplifiers, a lot of mixers, a lot of other components, right? Their degradation and in terms of how it all comes together. Now, is RF fingerprinting really new? Probably from space new, but is it a very classical, decade-old tech? Yeah. A lot of our classical ground-based terrestrial RF systems also have a fingerprinting. Now, I think that's sort of where the transition is, right? RF, the fingerprinting piece it sort of emerged as a hardware layer encryption with sort of the whole IoT and sort of proliferation of those kind of devices. That's where the need for something like this really emerged. It went to car fob keys and so on. What we've seen in the last couple of years is, and some of our work towards this has been in terms of sifting through a decade-long data set, something that's been in an open source. Data sets have been collected for AIS receivers, ADSB receivers, and we're talking about 10, 15, 20,000 receivers. Now to fingerprint these receivers and to find those signals in those legacy data sets, that's where a lot of interesting results have started coming up from a lot of American universities like Northeastern and a bunch of other RF-focused places, and we sort of work towards that as well. Very promising results in terms of fingerprinting. Sort of again, going back to a maritime focus, we're looking at commercial, civil, military, different kinds of assets. AIS spoofing is sort of the most common thing, right? If you're sort of indulging in dark activity or doing any non-state actor activities, so the first thing that happens is your AIS either gets spoofed or sort of you switch it off. What we call in terms of RF fingerprinting or RF geo-int is non-cooperative tracking. So these ships still have your X-band, S-band, maritime nav radars. They have L-band SATCOMs, KU-band SATCOMs that are on. Our payload will be able to detect these. So our coverage is from 100 megahertz to 18 gigahertz. So it covers a wide array of emitters, both in the naval sort of maritime domain, in the AD domain, and so on. We'll be able to geolocate them to a certain accuracy, again, function of latitude, sort of the angles at which we're receiving these signals and so on, and fingerprint them. So there's fair amount of effort that goes into collecting this data and then sort of fingerprinting and giving this information out. That's sort of where we are. Again, a newer sort of data set. RF data sets are not very common. They've not been generally in the commercial domain. It's only in the last 4-5 years that we're seeing a lot of commercial RF data sources that are emerging from, of course, the other continents. One interesting piece to look at is we've seen the recent Russia-Ukraine conflict. And in the current theater, as we all know, one of the first things that happens is the GNSS or GPS signals get jammed. Now, RF is the only probable sensor, RF sort of receiver that can really detect GPS interference, right? There isn't an imager, there isn't a hyperspectral imager, SAR, or any of those other sensors that can really pick up GPS interference areas and sort of what's the extent of GPS jamming and what should be your keep out areas and sort of your very strategic ingress, egress points and so on. So again, this layer is going to be extremely crucial for your other, not just space assets, but other terrestrial airborne assets to sort of start going and then sort of getting a deeper view of what the theater is. So with that, I think I'll be cognizant of...
Probably some question answers.
Yeah. Thanks for your time.
Thank you, Siddesh. Now, just picking up an example of needle in the haystack, I think best way to find it would be to jump on the haystack for a while. But, the problem is not finding a needle in the haystack. Problem is, if there are 1,000 needles in the haystack, to find the right one, which you are looking for it. So what happens is the signals is not one, there's not only one signal which is coming, there are multiple signals coming, so that is where fingerprinting becomes important. It started with naval application, where obviously there is one ship in very vast ocean and you can't really waste your optical or SAR efforts on that, looking for that vast area. So you say, okay, you pick up RF signal, which tips you or, provides you a cue, and that is where you launch the effort. Now it's becoming equally important for the land application also, because some of the companies that we interacted with had a capability for naval application, but not really on land application. So you see a very expensive missile system or potent missile system and you create a decoy, then only optical imagery or SAR imagery may not help detection for targeting. You have to know which actually is the live system and which is a decoy, which will be visible only if you detect some RF signal or some kind of signal coming out of that weapon system. Now, coming to our second speaker, Mr. Yogesh is the Vice President of Engineering at Astrogate Labs in Bengaluru. Astrogate Labs builds laser communication systems for terrestrial, fixed and maritime, and for air and space links. Previously, he was with Team Indus, working in the guidance and control team, and he's a master's from NTU, Singapore. Mr. Yogesh, and now I listed, data download and processing capability as one of the challenges. Now, your company has been working with lasers. Can laser communication systems with high bandwidth offer a solution to this problem?
Yeah. Thank you, Chair. Thank you, Marshal Bedi. Thanks for this opportunity. A pleasure to be here. So as Siddesh also alluded to, the drive has is something like conflicting requirements of miniaturization that primarily gets driven by the configuration of satellites being deployed are mostly not monolithic, very capable large ones, but distributed small ones. So the demands from in that consequence of that, each of those tend to have more capabilities in observing and remote sensing, and therefore the need comes to downlink those things to the ground, because with respect to the story the chair said, in the end all the information has to get aggregated to someone to in the end make a decision on something. So that is one of the problems, that is the problem for which we are trying to address. Typically, if I give an example of like nanosats and cubesats, because those are the ones who are going to see extensive launches in the coming years in terms of constellations and swarms. Typically, the data generation on board is on the order of hundreds of gigabytes per day per satellite. So now the constraint is to downlink them to Earth. Obviously, there is some advances in edge computing to do some processing online. But for the most part, the bulk of the heavy lifting of the processing is done on the ground, which means that there is a need to downlink it. And what we see is most of the time the data does not get downlinked, because typical RF systems on these class of satellites, the high data link can be an X band or Ka band. Typically they go up to 50 megabits per second, maybe 150 megabits per second. So beyond that, the demands on the host satellite itself to host high data rate communications becomes prohibitive. Either they consume more mass, or they have larger volumes, or they consume more power. So laser comm systems, because they operate at a terahertz spectrum, so inherently out of the gate they provide high bandwidth, and it's not a new technology. I just want to add that. And these have been in operational use with ESA, at least in using them for GEO to LEO crosslinks. But the miniaturization of lasercom payloads to service the needs of the constellation is what is an emerging new thing, which is what we are trying to address. So the current capability of the lasercom system that we are building, and a few others around the world, can provide typical data rates of about starting from 2.5 gigabits per second. What that means is 100 gigabytes of data, whatever the data it might be, imaging, multispectral, remote sensing, whatever, on a typical ground contact period of 7 minutes for LEO satellites, will take about upwards of 10 passes to downlink. So what that means is, the implications of that are, first of all, that somebody who is scheduling ground station time has to pay for that. There is this thing. Secondly, that much time is spent on the satellite itself instead of doing the imaging, which is a core purpose, that is being spent to downlink the data itself. So there is an opportunity cost there. And thirdly, the latency of the data from the time it got generated on board to someone to make the decision is increased, because it takes multiples of upwards of 10 passes to downlink the whole 10. The alternative is to discard a bunch of them, or compress them, or do some kind of compression on board. But that provided the hit you take is you might lose some insight which was there. So typically you would like to access the raw data as such on the ground. So lasercom systems for nano satellites, 2.5 gigabits per second upwards, but the what is enabling it now is that because the lasercom systems require the beam itself is very narrow. It's like a typical LEO to ground RF system footprint will be on hundreds of kilometers. The lasercom systems for us are 1 kilometer spot radius, which means that there is an inbuilt security aspect built in, because for anybody to intercept the signal, they literally have to be next to the receiver. So there is a very, very attractive use case for defense applications there. But the penalty you have to pay is to then the pointing and tracking becomes very, very crucial, because if you are not able to point the beams properly, then you miss the signal entirely. So that is some of the technology that we are working on, and basically the idea is to provide a free space link which is transparent to anybody's data, so that the time from when the data gets generated to somebody can act on it is reduced, and we don't lose any of the data which is generated on board, which might contain the insights that is needed. So that is what
Yeah, thank you very much. If two crucial capabilities can be achieved, that is faster communication and secure communication, then I think that's the and when it comes to limitation, I think any advancements will have some limitations, but the use cases are not binary in nature. It's not that if you switch to laser, then all your communications have to go to laser. So what happens is majority of it will remain the traditional way, and some crucial things can be resorted to this kind of communication in which those challenges can be overcome.
If I may add one final point, so where, as you pointed out, definitely optical comm is not a replacement for RF. There will be a need for low data rate and medium data rate links, this thing. But where it might provide significant value, and also I want to just point out that laser comm is a point-to-point communication. It's not a point-to-multipoint user like an RF, but where there is need for high throughput and security and less latency, for example, between AVAX platform to ground ship to an AVAX platform, not necessarily one transmitter to a multiple user case. So where the need for data to be aggregate, that's where it's really
absolutely useful. Thank you very much. Our third speaker on the panel is Mr. Ramesh Ganapalli, is the co-founder and CEO XT-Link Space Labs. Mr. Rupesh is a veteran in the aerospace and satellite industry. His company's mission is to revolutionize the space industry by providing ready-to-launch satellite platforms for global commercial and defense ISR space missions. Now, I must mention here that the company's first major milestone came with the successful launch of Janus-1, a software-defined 6U nanosat to demonstrate multi-tenancy payload capabilities developed in a record time of just 10 months and launched aboard ISRO's SSLV-2 rocket on February 10, 2023, which brought down the cost and time to space significantly compared to other traditional satellites. Well done, XT-Links. Now, Mr. Rupesh, when we talk of the sensors, there are many kinds, optical, IR, hyperspectral. Incidentally, just anecdotal information about hyperspectral. We were interacting with one of the security agencies, and somebody asked a very basic question to me that, sir, what is the difference between multispectral and hyperspectral? Because we keep hearing these things. Now, he says, can you, in a layman's term, explain me what is the difference between multispectral and hyperspectral? Now, that's quite a challenging job to explain this in a layman's term, but then I thought of an idea. So I told him, I said, it's like this. If you open my wardrobe, you will have one shade of maroon, one green, one yellow, one pink, etc., etc. But if you open that is multispectral. But if you open my wife's wardrobe, you will have hyperspectral, because it will be 50 shades of pink, 20 shades of blue, etc., etc. So hopefully he understood. Okay. So now, then the need, for miniaturization and secure communication. And now, Rupesh, your company has great plans for the future. Could you tell us how is XT-Link Space Labs poised for the future with space sensors, and what's in store with respect to advancements in them? Thank you. Yes, please.
Good afternoon, everybody. Thank you, SIA and Marshal Bedi for having me here. Today, So we at XD-Links, we are actually like, the idea of XD-Links is all about like building the platforms to like, bring in the right required infrastructure for like, various use cases. When I say platforms, both from like, satellite and the satellite bus and the payload. So we believe like, building that interoperability, managing and maintaining and keeping that control of the interface with the sensors and the bus is what is the critical thing to kind of, achieve the ConOps, what is required to like, plan for any mission to actually operate and then, derive the end use case of the, the space utilization. So with that objective at XD-Links, we have undertaken building the various bus platforms, like ranging between 10 kg to 200 kg, primarily in the LEO orbits. And also, like at the same time, parallelly, like, we've taken a task to like build some payloads to actually configure that both the payloads and bus platforms together to offer a fully functional satellite as service to enable like, multiple global and ISR, like, the satellite missions to bring into the space. So on the payload side, I think the topic is today about the payloads. So we have, we have actually taken up the core fundamentals of like, of developing the payloads by going with the approach of building the core bottom layer of the, technology, both from the photon-based capture and then sensing and the microwave-based sensing. So on the photon-based, so we have started like building, we started with building like, the few payloads with the sensors identified and, indigenously developed the required cameras with the camera electronics and the, the compute options, and integrate the, primarily we started with the MSI, like multispectral with the 7 bands as like, the core base offering on the MSI side. And also like we kind of have the plans to like, expand that capability towards the real hyperspectral with the greater technology where like, we can achieve the kind of SNR required to actually like, have the signatures required to sense the objects what we primarily, ultimately want to sense it. On the microwave side, like, we have started building on again like with the fundamental, foundational approach by just developing our own baseband SDR. Basically, that baseband SDR is like what we are converting to leverage the baseband SDR to like, make the various comms modules, like, the typical radios like S-band, X-band, K-band, and also the same baseband SDR is being currently used to like, develop our own signal intelligence payload element within that like, frequency ranges. So apart from that, recently like, we have taken up a challenge from a customer to develop a E-band payload, which is like, with very higher frequency band, where like, the customer has the, the spectrum rights and like, it's a BIU primarily to develop and demonstrate and operate this payload in space to kind of like, preserve that spectrum rights like above 5 years. So that E-band payload was collaboratively developed between XD-Links and then a couple of technology partners from UK. And this is the world's first, space grade miniaturized E-band, which is going to be, which were developed by XD-Links and tested, ground tested and like aerial tested, and which was integrated with our one of the smallest satellite bus platform, XD-Links NS, and which is now on the, which is currently on Transport 12 SpaceX, which is going to be launched next week, basically. So we are excited about the 14th launch and fingers crossed. And this is the first attempt in getting that E-band. And E-band, I think, as my co-panelist mentioned about the laser comms. So the way I see, like, we do, I think the need is for, like, achieving the higher data rates and, like, higher throughputs. So now, while this laser comms being, like, one of the options explored, and of course, with its own challenges and pointing accuracy and weather conditions and all. And we do believe like E-band could be actually a complementary RF band to achieve that higher data rates. Especially like we are kind of like foreseeing the usage of E-band would be like much significant, especially with the ISL, in transmitting the data across the orbits. From LEO to MEO, MEO to GEO, and then like from GEO to ground through the existing transponders, basically. So that is the that is the one technology we have taken up a at the roadmap, and we're launching that very first, very basic, data rates, which we are targeting just to establish the connection and link, and calibrate the link margins what we established next week. On the optical side, so we have plans to develop the idea is to optimize the size of the optical lenses with the sensors what we are identifying to achieve that the kind of resolutions what we want to achieve basically, and the SNR. And so in that process, we started working on 190 millimeters aperture class, with which we're targeting 1.5 meters, sub 1.5 meters as a pan native GSD with the multispectral. And the idea is to expand and scale the same concept of that optics to 350 millimeters, that is sub 0.7, 70 centimeters, and also we have plans to scale it to a bit to make that working in conjunction with the bus to operate that satellite in the VLEO to achieve the kind of data rates, the kind of resolutions like sub 30 meters and 30 centimeters within that the similar form factor payloads basically. That is on the MSI side, and then hyperspectral also we have the concept design developed, and we are currently working with. See, in this process, the key approach what we are taking is not necessarily though we claim we are doing a lot of things, but not necessarily we are trying to do everything by ourselves. We are actually working with various technology partners from optical manufacturing, fabrication, polishing, and also identifying some sensors where sensors can be enhanced to meet our swath and the resolution requirement. So we are kind of trying to work out backwards with the technology players, the technology suppliers, kind of driving the specs to define the newer generation sensors to integrate them into our satellite platforms.
Thank you. Thank you very much, Rupesh. Indeed, very impressive and important point of collaboration that he brought out. I suppose, colloquially speaking, the aim is not to win a Nobel Prize or something. Idea is to produce a product, and if it takes collaborating with the sister industry, then I think that's the way to go. Thank you very much, Rupesh. Now, we started a little late, and I just wanted to tell you that going by my past experience, there must be equal number of people present already in the lunch hall, So you might as well wait 10 minutes while they make space for you. We have fourth speaker, Mr. Rakshit with us. He is the VP of Product and co-founder at Galaxy Space and alumnus of the Indian Institute of Technology, Madras. His journey into cutting-edge technology began with the Avishkar Hyperloop project. Their prototype earned them a spot in the finals of the SpaceX Hyperloop pod competition in 2019, where it was presented to Mr. Elon Musk. Following a brief stint at Siemens Technology, where he developed AI-powered cognitive intelligence systems, Rakshit co-founded Galaxy, a company building the world's first SAR plus EO satellite, a multi-sensory system. Now, Mr. Rakshit, can you explain why this sensor is critical and how it enhances intelligence in the broader context of ISR?
Right. Thank you, Bedi sir. Yes. And it's a pleasure to be here with these fellow panelists. And good afternoon, everyone. So, it's great that we are at this juncture right now where space is getting democratized and accessible to everyone, right? Because of the democratization of launches and then the satellite bus. But I think at the same time, if we want to strengthen the ISR capabilities, sovereign ISR capabilities, right? I think there has to be a wave of innovation at the sensing level. So each geography and each nation have its own set of sensing requirements depending upon, geographical nature of that particular nation. And I think Mission Drishti is one such innovation by Galaxy Space, which is specifically tailored to the requirements of the ISR requirements of, our own country, right? And the first generation Mission Drishti satellite is going to go into the orbit in October 2025. Some elements of the satellite were also tested in the SpaceX mission that was launched on the 31st of December last year. And I'll just brief a little bit into what exactly is Mission Drishti and what is the objective of the first generation of Mission Drishti satellite, right? So the idea is that we want to provide satellite data which is consistent, reliable, and interpretable, irrespective of the environmental and the weather conditions or the nature of the terrain, on any location in the country, right, or globally, right? So with the current sensing capabilities that we already have, one of the biggest issue is that the sensing that the data that we capture, right, it fluctuates a lot with respect to the environmental conditions and the weather, right? And thus there is an inherent difficulty in building the decision support systems or providing consistent actionable intelligence which is also timely, right? So how Mission Drishti bridges this gap is that it puts two sensors, which is a synthetic aperture radar sensor and a multispectral sensor, on the same platform, and it synchronously fuses the capabilities of both of these sensors, right? So SAR having its all-time, all-weather mapping capabilities, and multispectral, of course, as we know, is its intuitive and interpretable nature, right? And thus, by mixing these two sensors, putting them upon the same platform and synchronously fusing them, we are able to produce a third category of data, which is called as the sync-fused SAR data, right? Now, the sync-fused SAR data will be available over any location at any point of time, irrespective of the environmental and the weather conditions over that region, right? And I think we want this to become the one-stop, data solution for all the image intelligence requirements. And ultimately, the idea is to build a decision support system which can provide consistent and timely analysis, right? We really don't want to get into the trap of not being able, because data is the fundamental and the foundation layer over which everything else is built, right? So we really don't want to get into the trap of, building complex systems because the data itself is not consistent and not reliable, and it's really complex, right? So we really want to solve that data problem where we produce that one unified source of data, which can be easily interpreted by a user, which can be easily ingested by a system on which AI models can be trained. One AI model can be trained for multiple problems, and you don't have to train 50 AI models, right? That sort of complexity. And of course, in the future, in the subsequent generations of Mission Drishti satellite, we want to integrate more sensors like AIS or electronic intelligence sensors, and so that we ultimately want to move towards being able to provide the actionable intelligence in real time, right? I think that is going to be the next step for us, and I think that's our effort to kind of take our ISR capabilities to the next level.
Thank you very much. We all know the limitations of optical systems. Any clouding, etc. comes, then you can't see the ground, or you take pure SAR data, you can't really interpret it without the help of an optical image of that place earlier. Now, if these two things were to be done simultaneously and continuously fused, I think we are definitely getting into new thing. And interoperability is very, very important, because now different companies are opening up. And if someone has to create some kind of analysis model, then every feed should be able to go into that. Otherwise, even services can't now hire 10, 20 models, which will interpret different things. So that's very, very important. I think I'll stop here. Thank you very much, panelists. And now we open, yes, please, a few questions for 5-7 minutes, please.
Do I get a microphone, or you understand me? I can speak loud. Thank you. Okay. Thank you. Very good panel. Very happy to be here again, because now it's the first time the circle closest for me what we discussed last DefSAT, and this was in formations, in constellations, in swarms, in miniaturization, and so on. However, I didn't hear much about it the last 3 days. Now, thank you to bringing it up, but I think we'd have to be precise. If we talk about constellation and then swarms and cloud, what we are missing is formations. Yeah, because that is the tricky thing. Flying satellites in relation to each other's position. And that is, I think, what is bringing the accuracy and the needed quality of picture the end customers looking here for. I have not heard what is the outcome of the 2024 challenge which was launched. It was not 2010 when the whole thing started. I have a colleague and business partner. He was lecturing in 2008, one of the biggest defense organizations already in flying formations, swarms, clouds. Yeah? ESA, they had a cluster mission a long time ago before NASA. So I think there's a gap here in understanding what has been done, how challenging it is to fly formations with CubeSats or bigger satellites. It's maybe easier because the positioning is the key thing to keep. But maybe I take it with the chair and we find out how we can contribute, because I was helping to establish a company in India some years ago, and I really having difficulties to get to the point where I understand how we can help. We are open in supporting India's needs, but we need to understand how we can help. And I know you startups here, these are all startups now. You are doing your very best, but there are people working since 20 years, 30 years on such things. And ISRO is also a very strong space agency, no doubt. But this is a challenging effort. And I think where you want to make a difference, you need to go into these niche markets, into these specifics to enhance your operational qualities. And I'm happy to discuss that later on. Only want to say thank you very much to bringing it up. Yeah.
Thank you. Yes, please.
Good afternoon. I'm Captain K.K. Agnihotri. I'm from the National Maritime Foundation. My question is to Mr. Rakshit. It's a very basic question with regard to mechanics of how you go about doing simultaneous imagery of electro-optical as well as SAR, because my understanding is SAR is you have to have a beam-on aspect, while electro-optical you have to be having a look-down aspect. So how do you get the same time-stamped imagery of same spatial domain and fuse it? So
two different sensors there, right?
Yeah.
Two different sensors, but the SAR sensor is looking at beam-on aspect. Maybe you have to make two passes if conventional wisdom goes.
Yeah, I understand.
Yeah. So that's a very good question, sir. So there's the concept of real swath and virtual swath for both the sensors, right? And basically they are able to, the virtual swath is basically that they are able to look in a certain field of view, right? Depending on the satellite maneuverability, you can make them look from, let's say, plus minus 10 degrees, 15 degrees to, or plus minus 35 degrees to each side of the satellite, right? So we have positioned both the sensors mechanically, we have positioned both the sensors and in such a way that the virtual swath of both these sensors intersect with each other to some extent, right? So if the virtual swath of EO is like 150 kilometers and virtual swath of SAR is like again 150 kilometers, part of it, let's say 30 kilometers, intersect with each other, and we operate the satellite, we align the satellite in a way that we are able to image the regions which fall in this intersection, right? So the real swath of the satellite falls in some inclination, right? So what happens is, actually in simple words, both the sensors are looking off nadir, because SAR can map off nadir, and the quality of SAR data improves as you keep looking off nadir, and optical can look off nadir, but the quality of optical data keeps decreasing as you look off nadir. So you have to find that sweet spot where both of these sensors can capture the image, which you can further refine, the quality of which you need to further refine during the data processing. So that's what we are doing.
Yeah, thank you. Actually, precisely what I was hinting at, the demands, they stretch in opposite directions. Like very rightly, SAR, because synthetically it's increasing aperture of the radar, so it needs to have a greater offlook, whereas optical starts reducing. So overlap is what you mean, that they have some kind of overlap, right?
Yes.
Which is being used. And any more questions, please? Yes, please.
Sir, good afternoon to you. This is Group Captain Vishnu Bajpayee. I have a query. For laser communication, what you have been mentioning, from LEO satellite, like bandwidth is very high. You want a high data rate. In a single pass, it's going to dump. Did you carry out any survey which place in India suits this location?
Yeah.
Irrespective of atmosphere, and out of 365 days, how many clear days you can get?
Yeah. So, lasercom, there is a definite vulnerability, which is that its signal will attenuate severely if you go through clouds or fog. So the way to mitigate that is to typically locate the ground station in the first place on drier sites. In India, typically from our analysis, we have found Mount Abu is a good site to host it. And probably even Ladakh, the Hanle Observatory is there. So those are typically high altitude. In general, you can say sites that are good for optical astronomy are good for lasercom, because the weather is dry. The cloud coverage for most of the year is not there significantly. Other than that, one other aspect, so these are India sites. In India, these are the couple of sites which seem to be the best for locating near cities is not a good idea because of light pollution and so on. But having said that, because there is a attenuation of the signal, if you have cloud coverage, so what is typically done is to have ground station diversity, in the sense locate multiple ground stations around the world in drier sites. So other good sites from our analysis are Western Australia, somewhere near Perth, and Santiago near Chile, where there are a lot of optical sites. So the idea is you can use, if you are in a given pass unable to downlink on this thing, you can downlink to any of the other sites. So that is the idea. And potentially, because since there are many such ground stations coming up, interoperability. So if you cannot downlink to our ground station, the Astrogate Labs ground station, you can still downlink to a partner ground station and then relay it back to. So that is an option.
That answers my question. I'll come back to you during the lunch time. Thank you very much.
That's all. Thank you very much. Last question. Can we take last question? Okay, please. Yeah, make it brief.
Yes, sir. What is the highest peak rate you are reaching? So our throughput currently in our system, which we have demonstrated, is 1 Gbps terrestrial up to 3 kilometers. The ground space to ground link, for which we are working with ISRO, that can go up to 2.5 Gbps downlink. And potentially, we anticipate without too much hardware change, 10 Gbps should be achievable for space to ground links. No, those are without losses. Those are without losses, yes.
Okay, thank you very much, ladies and gentlemen. Please join me in giving a hand to all the efficient panelists. Thank you very much.
Thank you very much, panel. We can have a group picture before we proceed.